Hi, welcome to my YouTube channel Pharma Chem Vibes, presenting before you how to interpret infrared spectrum at the basic level. So this video is particularly created for those students who keep running away from structural elucidation part. They either find it difficult, they think it is about by hearting a lot of numbers and they feel that they won't be able to do it. So they slowly start losing interest and they miss the fun. So this particular basic level is designed to help such students who find it difficult to understand structural elucidation. What role IR spectrum has to play? If you know the drug, then IR serves for identification. Every pharmacopoeia mentions infrared spectrometry as the first and foremost identification test which cannot be substituted by any other analytical technique. But if you do not know about the substance, if it is unknown for you, then IR will reveal information about functional groups and along with other sophisticated techniques like mass and NMR, it will help you to deduce complete structure. IR spectrum is like identification of a compound, and spectrum doesn't only mean the numbers which students keep on by hearting, but there is a lot about where does these peak appears, at which wave numbers, what are their intensities, whether the peaks are strong, medium, weak, how are their shapes, whether they are broad, very broad, or whether they are sharp. So rather than just reporting the numbers, you need to also look at how does that peak look like. And IR literally scans the compound, so nothing is hidden. And if your sample preparation is good, IR spectrum will never lie. It will reveal those minute details about your compound very quickly, which is not possible by other techniques. So in this basic level, we are going to learn what is there on this spectrum scale, what is there on the X and Y axis, then what are fingerprint and functional group regions, why IR spectrum is called as a fingerprint. Then positions, shapes and intensities of following functional groups as well as different bonds, CH stretches and bends, so alkanes, alkenes and alkynes, C double bond C, C triple bond C and C triple bond N stretches, so alkynes and nitrides, C double bond O and C single bond O stretches, so various carbonyl functional groups like aldehydes, ketones, acids, amides, esters. C single bond O means hydroxy compounds or ethers. OH and NH stretches, so amines and again hydroxy compounds. So if you regularly revise the contents given in this video or just repeatedly see it consecutively for 15 days, you'll be able to develop a basic confidence in interpreting the IR spectra. Because we are directly switching on the spectra, it is advised that you should read the theory from the books to understand from where this spectra originates. So like any other spectrum, IR spectra is a plot. It is a two-dimensional plot having wave numbers on the x-axis and percent transmittance on the y-axis. Usually in the other spectrometric techniques, the simplest form UV, we have wavelength on the x-axis. If you convert wavelength into centimeters, and reciprocal of this wavelength expressed in centimeter, it becomes wave number. So wave numbers are usually bigger values than wavelengths. And because we have so many closely related peaks in the IR, these bigger values helps to distinguish between them, because wavelength is smaller in case of IR. IR radiation is weak, so absorbance is weak, transmittance is strong. So on the y-axis there is plot of percentage transmittance. So IR spectra looks like reverse than the normal spectra generated by say UV, NMR, MAS. Peaks in these techniques, they are straight, while in IR they are inverted. Spectrum starts from the top, it comes down, that is called as a peak. Now the total spectrum starts from 400 centimeter inverse and ends at 4000 centimeter inverse. Though different FTIR instruments allow you to record the spectrum till 1000 centimeter inverse also. Pharmaceutical drugs, those organic compounds, they mostly show peaks between this 400 to 4000 centimeter inverse, which is the mid IR region. And this transmittance scale may be given in the percentage starting from 100 at the top or 1 at the top coming to 0 at the bottom. Now this spectra from 400 to 4000 is divided into main two regions, and that boundary line is at 1400. So 400, 1400, 4000. So the region from 400 to 1400 is called as a fingerprint region. It is called as a fingerprint because as every individual has a fingerprint which does not match with other individuals, and that is why we use biometric system for identification of different persons. Likewise, we can use this fingerprint region because the peaks which appear in this region, they are very much specific for each compound, so they can be used for identification. They are not interpreted. You just need to overlay and match two substances, their spectra, and see how much overlap they are having. If they match perfectly, it means these two spectra are coming from the same substance. That is why every pharmacopoeia mentions infrared peaks spectrum for identification of the compounds. Still, there are two important vibrations which come in this region. They are C single bond O stretch and some vibrations which are observed in the monosubstituted and disubstituted benzenes. Even we can distinguish between them. Only these two vibrations are of importance with respect to structural elucidation. Rest all region, that is from 1400 to 4000, it is called as functional group region. Many important functional groups which are commonly observed in drug molecules, they come in this functional group region, and it is very specific about their shapes and intensities. So let's get into it. We can learn interpreting IR spectra by two ways. Either we can look at the spectra and then try to deduce from where peaks have appeared, or we can take some structure and then observe the functional groups, learn where they appear and try to locate their peak positions and shapes. So this is the hypothetical molecule which I have drawn because it contains majority of the functional groups which we are going to learn in the basic level. If you want to predict what will be the IR spectra of this compound. You will have to closely look which all bonds are present. Like this CH3 is actually comprised of 3 single bonds with the H. Similarly, this oxygen is bonded with the H. Here nitrogen is bonded with 2 bonds with the H. There are some other points which also can be drawn in the form of carbon and number of hydrogens which are attached to them based upon its valency. Like here, this carbon has 2 bonds, so it will be CH2 because valency of carbon is 4. But here, carbon has already completed 4 bonds, so it will be only carbon. 5 carbon atoms are substituted. So in this benzene ring, there is only 1 carbon which is having hydrogen. So this particular structure contains alkyl substituents, hydroxy, then acid, then amine. This is nothing but double bonds, then triple bond. So starting with the simplest one, and 100% they will be present in every IR spectrum. It is because they are originating from carbon and hydrogen. Because organic molecules, they are necessarily hydrocarbons. So every organic compound will be containing at least 1 carbon and hydrogen. That is why in every IR spectra, whenever it will come in front of you, you need to first look at CH stretches. They appear around 3000 centimeter inverse. In the next level, because now we are at the basic level, in the next level we will see different kinds of CH stretches originating from alkane, alkene and alkyne, representing various sp, then sp2, sp3 hybridized carbon atoms. We will be looking how they differ from each other. But for now, these CH stretches, they always appear somewhere around 3000, either before or just after it, say 2900 or 3050, just before and just above 3000 centimeter inverse, we will be having CH stretches. Their speciality is they always appear in the form of cluster. These peaks are not sharp. It looks like there are so many peaks which have merged together. There are many because every compound contains at least 2 or 3 such CH bonds. So there are many peaks which have merged together. Their intensity will depend upon how many such CH groups are there. If it is just alkyl and there are, say it's a long chain compound, then there will be a significant height of this peak. So their intensity in the IR spectrum means the height of this peak from the top, how much it extends to the bottom. So by looking at the height of this peak, you will also come to know whether this compound contains a lot of CH or there are only very few. So CH stretches we have learned, they will come around 3000 and they will be in the form of clusters. They will appear like number of peaks have combined together, and their height will tell you how many of such CH are present. In the next level, we will learn to distinguish between different kinds of CH stretches. Now coming to CH bends. Usually stretching requires more energy, so they come at higher values. Bending requires lesser energy, they come at lesser wave numbers. So CH bends, they also are in the form of clusters, but intensity is low as compared to the stretches. They appear around 1300 and 1400. So there can be values. You need not to by heart the actual numbers. There can be 1350, 1390 or 1450. Any value around 1300 and 1400 will be belonging to, if they are in the form of clusters, it will be belonging to CH bends. So whether compound given to you is organic or not, you can quickly test it whether there are peaks around 3000 and 1300. See, single bond C stretches usually go into the fingerprint region and they are not observed. Theoretically, they come at 1200, but they are never interpreted. But C double bond C, they are important. So because this is a benzene, there are 3 double bonds. Even in the straight chain compounds which are containing double bonds, they will give rise to C double bond C stretch, which will be coming around 1600. They are of medium intensity, and the specialty about them is they give rise to overtones. Now in the next levels of advanced, we will be learning what are overtones, combination tones, but for now just remember they will give rise to number of small peaks at the top. They are usually starting from 1660 and they go up to 2000, and they roughly indicate how many number of double bonds are present. Like here we have 3 double bonds, so we have 3 overtones. This is applicable to only simple molecules. If there is alkene containing only 1 double bond, there will be only 1 overtone. See, triple bond C stretch. This is very rare to observe. Even C triple bond C and C triple bond N. These both stretches, they appear around 2200. I have said around because there can be value like 2150 also or 2350 also. So a broad range would be 2100 to 2300, but you can remember it is coming around 2200, and they are usually of low to medium intensity, but they are very sharp, they are very fine as compared to the other peaks. And usually this region in the IR is not occupied by any other peaks. There are no competitors. There are no other functional groups which can appear in this region. So if you have only values or if you have spectra in front of you, you can easily recognize if there is any peak between 2100 to 2300, it is surely because of a triple bond. Then about OH stretches. Now OH can be present as a hydroxy, that is alcohol or phenolic compound, or it can be in the form of COH, that is acid. OH peaks are usually broad and they are strong. So they are wide. Hydroxy OH, that is alcohol, it has a round tip. It is very symmetric and good intensity, strong peak. But if this OH is a part of carboxylic acid, then it turns somewhat asymmetric. Still, it has that round shape, but because it has merged with the CH stretches, its shape seems to be somewhat asymmetric. And there is a very broad range from 3100 to 3600. Peaks are very broad. So OH stretches can be distinguished easily whether they are hydroxy or whether they are acid. Hydroxy is a round and With the acid, it is asymmetric. With hydrogen bonding, still it will become more broad. Then coming to the most important type of peak, C double bond O stretch. Many people start interpreting IR spectrum from this CO stretch. They look for the presence or absence of this peak, and perhaps this is the most prominent type of peak observed. So this C double bond O, that is a carbonyl stretch, it always appears somewhere around 1700. So you can say roughly at the middle of the spectrum, and between 1600 to 1800, somewhere around 1700, we have a very strong absorption peak because of the carbonyl group. Now there are several kinds of carbonyl groups which you know. There are amides, CONH2. In case of amides, it comes before 1700. It may start at 1650, 60, 70, 80 or 1690 also, but it will be surely before 1700. In case of acids and ketone, it comes roughly with 1715, but in case of aldehyde 1730, and in case of ester it goes bit long around 1745. So higher and lower levels indicates ester and amides respectively, and in between we have some other tests by which we can distinguish whether it is aldehyde, acid or ketone. Just now we have seen if you have a problem of distinguishing between acid and ketone, just now we have seen acid will also give you OH stretch. In case of ketone it will be absent. So there is no need to distinguish between them. Even aldehyde will be lacking it, that OH stretch. So it will be easy to distinguish between aldehydes, acids and ketones, while amides and esters, by their values only, they will be ruled out from your structural elucidation problem. So a good length of this prominent C double bond O stretch can be observed. Then as we have just now talked about C double bond O stretch, let's now see C single bond O stretch. This goes into the fingerprint region, because we have seen till 1400 there is a fingerprint region. This is the only prominent peak observed for C single bond O, which goes in the fingerprint region. It is having good intensity and it can vary from 1000 to 1300. So any value, say 1050 or 1200, 1150, that will indicate there is a carbon which is bonded to an oxygen with a single bond. So it is also present in case of acids as well as esters and ethers, alcohols. So this is again most of the times present in the organic compounds like CH stretches. Then we have NH stretch. With NH stretch, they also have a wide range, that is from 3300 to 3400. Now because this compound, I have included all the functional groups. Here we have OH stretch also, and their areas overlap, because for OH stretch we have seen it is coming from 3100 to 3500 or 3600 in some cases. So usually these two peaks merge with each other. So if they are present together, then intensity of this NH stretch will appear stronger. If OH is not present, if it is just amine, then this sharp peak will appear at the top. Usually NH stretches, they have very weak intensity than the OH stretches, but because now it has come together with OH, it is having strong intensity. And there is very easy interpretation whether it's a primary amine or secondary amine or tertiary amine, because it is NH stretch. In primary amine, we know it is NH2, like it is shown in this example. So if it is a primary amine having two NH stretches, we will have a doublet, means two peaks. Whereas if it is a secondary amine where this H will be substituted with say methyl group, then it will have only one peak. Call it as singlet. And if it is a tertiary amine wherein both the hydrogens are substituted with some R group, then there is no NH. So it doesn't give any peak. So IR spectra can easily tell whether it is primary amine, secondary amine or tertiary amine. Now this was the very basic level. Still there are so many things to be learned in the interpretation of IR, but we will take it in the next levels. So in the advanced level, you will be getting to know how to distinguish between CH stretches into the alkanes, alkenes and alkynes. What do we mean by Fermi resonance? How can we see peaks of, if it is a liquid IR, then peaks of the solvent, if there is a lot of CO2 accumulated in the sample chamber, then how it gives rise to peaks. And in the fingerprint region, how to distinguish between mono substituted benzenes and various disubstituted, that is ortho, meta, para types of benzenes. All the information which we just now have seen, this is ideal case condition. There are a lot of factors which affect these IR frequencies. So these numbers are not fixed. They can get changed based upon the chemical environment, and that is the beauty in fact, because if you are carrying out some synthesis wherein you are changing the functional groups, then you will be easily able to see the effect of the new neighboring groups on your structure. So thank you for listening. If you have any doubts, please write in the comment section or you can contact me personally. But this interpretation part is very much necessary no matter in which branch you are. Either you are pursuing your education in the pharmaceutics or pharmacology or pharmaceutical chemistry, everywhere you will be needing this characterization part, and IR in that way is very much predictable, and with practice you can learn it very easily. Thank you.